Every galaxy in the universe but one can be photographed whole, turned face-on or edge-on, catalogued, measured from the outside. The Milky Way is the exception. We live inside its disk, roughly 2/3 of the way out from the center, peering through veils of gas and dust that hide most of the light from the far side of the galaxy. This vantage is both a curse and a gift. It denies us any God's eye portrait of our own home, but it lets us measure individual stars, gas clouds, and orbits with a precision no external galaxy allows. Galactic astronomy is therefore the strange art of reconstructing a vast three-dimensional structure from the inside out, assembling, from the distances, motions, and chemistry of millions of individual stars, the shape of the great barred spiral in which we are embedded. That structure, mapped over a century, is a barred spiral galaxy, a flattened, rotating disk of stars a few tens of thousands of light-years across, a central bar and bulge of older stars, a sparse, roughly spherical halo, and, enveloping and outweighing all of it, a vast dark matter halo whose presence is felt only through gravity. The Sun sits in the disk at a distance now measured to remarkable precision, about 8.1 kiloparsecs from the center, some 26,000 light-years, fixed by tracking a single star's orbit around the central black hole. And the Sun is itself in motion, sweeping around the galaxy at some 230 kilometers a second and completing one full circuit, a galactic year, in roughly 220 million years. In the whole of the dinosaurs' long reign, the Sun did not manage even a single lap of its own galaxy. The galaxy's luminous body is above all its disk, and that disk is really two overlapping populations. The thin disk, only a few hundred light-years thick at the Sun's location, holds the younger, more metal-rich stars, moving on calm near-circular orbits, and it contains the spiral arms, the molecular clouds, and essentially all the ongoing star formation. Threaded through it and reaching well above and below is the thick disk, older stars, more than 10 billion years of age, poorer, in heavy elements moving on hotter, more plunging orbits. The two are distinguished not just by shape but by chemistry. The thick disk is enhanced in the so-called alpha elements, the fingerprint of rapid early enrichment by exploding massive stars. The leading interpretation is that the thick disk is a relic of the galaxy's turbulent youth. Stirred up and thickened by the last great collision, the Milky Way endured, an event whose fingerprints we will meet again in the halo. The disk is not only stars. Woven among them is the interstellar medium, the gas and dust that, though a mere few % of the disk's mass, is the raw material of every star yet to be born and the ledger in which the galaxy's chemical history is written. It exists in several phases at once. Cold, dense molecular hydrogen, gathered into giant clouds along the arms, is where gravity finally overcomes turbulence and new stars ignite. A warmer, more extended layer of atomic hydrogen, observed directly through its 21-centimeter radio line, which passes unimpeded through the dust that blocks starlight, was the very tool with which the galaxy's rotation and spiral shape were first mapped. And a hot ionized phase, glowing around young stars and pervading the space between, completes the cycle by which gas becomes stars, and stars, dying, return their enriched gas to the whole. Toward the center, the disk gives way to a thicker, older, more crowded concentration of stars, and here the modern picture is sharper than the old word bulge suggests. Infrared surveys that pierce the dust and precise star counts have revealed that the Milky Way is a barred galaxy. Its heart is a boxy, peanut-shaped bulge sitting atop an elongated stellar bar, whose long axis is tilted away from our line of sight and which stretches perhaps 15,000 light-years end to end. The bar is not a fixed shape but a coherent, rotating pattern, sweeping around at a well-measured rate. Most of these central stars are ancient and chemically varied, which argues that the bulge was not made in one early burst, but built up gradually, secularly out of disk material, that the bar funneled inward and thickened. A pseudo-bulge grown from the galaxy's own disk rather than dropped in by some primordial collapse. At the very dynamical heart of the galaxy lies a compact radio source called Sagittarius A star, discovered in 1974 and long suspected of marking a supermassive black hole. The proof and the measurement of its mass is among the most rigorous achievements in all of modern astrophysics, and it earned the 2020 Nobel Prize in Physics for Reinhard Genzel and Andrea Ghez. The decisive method was to watch individual stars swing around the unseen central mass. One star, known as S2, follows a stretched, eccentric orbit with a period of about 16 years, whipping to within 120 times the Earth-Sun distance of the center at its closest approach and reaching speeds of thousands of kilometers a second. Decades of infrared monitoring, and since 2017, the Ford telescope gravity interferometer, have charted that orbit with breathtaking precision, and Newton's laws then demand a mass of about 4 million suns packed into a volume smaller than the orbit, a density no cluster of ordinary stars could survive. The only viable explanation is a single black hole of about 4.3 million solar masses, and the same exquisite orbit has delivered 2 landmark tests of general relativity in a place no laboratory can reach. At S2's closest approach, the team detected the gravitational redshift of its light. The reddening a photon suffers as it climbs out of a deep gravitational well, precisely as Einstein's theory predicts, and they detected the slow rotation of the orbit's ellipse itself, the same Schwarzschild precession that famously wheels the orbit of Mercury around the Sun, here turning in the fierce gravity of a 4 million solar mass hole by exactly the amount general relativity demands. The star traces, in effect, a delicate rosette around the darkness at the galaxy's core, and every loop of it confirms Einstein anew. The black hole's true edge, its Schwarzschild radius, is only about 1/10 of the Earth-Sun distance, which at the distance of the galactic center subtends a mere 10 millionths of an arcsecond on the sky, at the very limit of the possible. Yet in 2022 it was imaged. The Event Horizon Telescope, a global network of millimeter radio dishes linked into a single Earth-sized instrument, published the first picture of Sagittarius A star's shadow, a bright, asymmetric ring of emission surrounding a central darkness, of exactly the size predicted for a 4 million solar mass black hole at 8 kiloparsecs. Follow-up images in polarized light revealed ordered, spiraling magnetic fields threading the very edge of the hole. And, yet for all its mass, our central black hole is a famished, dormant thing, accreting a mere trickle of matter, flickering only in occasional flares. The Milky Way does not blaze as an active galaxy, its monster sleeps. Seen from above, as we can only infer, never directly observe, the disk is patterned with spiral arms, ridges of enhanced density where gas piles up, clouds collapse and hot young stars trace out bright lanes. Because dust hides the arms, behind the galactic center, mapping our own spiral structure is far harder than mapping a distant galaxy, and for decades the number and shape of the arms were fiercely contested. The breakthrough came from measuring direct, trigonometric distances to the radio beacons called masers that light up regions of massive star formation. A dedicated survey charted some 200 of these with parallaxes accurate to a few percent, and assembled the most reliable map of the galaxy's spiral structure yet made. It shows several principal arms, among them the Scutum Centaurus, the Sagittarius Carina, the Perseus, and the Norma arms, with the Sun tucked into a substantial local arm of its own, and it revealed that several of these arms appear to spring from the very ends of the central bar. What the arms actually are remains a deep question. The classic answer is density wave theory. The arms are long-lived patterns that rotate as a coherent wave at their own fixed speed, distinct from the stars and gas, which flow through them like cars easing through a traffic jam, compressed, shocked into forming stars, and released out the far side. A competing and increasingly favored view holds that many arms are instead transient and material, self-gravitating over densities that wind up, dissolve, and reform every few 100 million years. The rich six-dimensional map of stellar motions from the Gaia mission has revealed that the disk near the Sun is full of kinematic ripples and phase spirals, signs of a disk still ringing from a recent disturbance, which complicates any tidy, steady-state picture. Reconciling the two views and settling even how many arms the Milky Way truly has remains genuinely open. Surrounding the disk and bulge is the stellar halo, a sparse, roughly spherical scattering of old, metal-poor stars, globular clusters, and the shredded debris of swallowed galaxies. It holds only about 1% of the galaxy's stars, but it is dynamically priceless because its stars are ancient, loosely bound, and retain a memory of how the galaxy was built. They move on a wild range of orbits, many steeply eccentric, some even retrograde, circling against the disk's rotation, in stark contrast to the orderly wheeling of the disk. And the modern hierarchical picture of how galaxies grow predicts exactly this, that great galaxies are assembled by devouring smaller ones, and that the halo is in large part the graveyard of those meals. The Milky Way's halo bears this out spectacularly. In 2018, analyses of data from the Gaia mission uncovered a vast population of inner halo stars, all moving on strongly radial, plunging orbits with a distinctive chemistry, the shredded remains of a single massive dwarf galaxy, now called Gaia Enceladus, or the Gaia sausage for its shape in the map of velocities, that the Milky Way swallowed some 8 to 11 billion years ago. That single ancient collision delivered perhaps 2/3 of the inner stellar halo, and is thought to have dynamically heated the young galaxy's disk, very likely creating, or at least thickening, the thick disk we met earlier. In one stroke, the Gaia data turned a vague theory of hierarchical assembly into a specific, datable event in our galaxy's own biography. Beyond that dominant merger, the halo is laced with stellar streams, the tidal tails of globular clusters and dwarf galaxies being slowly pulled apart as they orbit. The Sagittarius dwarf, currently being torn to pieces, wraps a colossal stream of stars right around the sky, and the thin, cold streams of clusters act as exquisitely sensitive tripwires, for a gap or a kink in a stream can betray the passage of an unseen lump of dark matter. The globular clusters themselves, about 150 of them, include some of the oldest objects in the galaxy, near 13 billion years of age, and so set a hard floor beneath the age of the Milky Way and once of the universe itself. The halo, in short, is the galaxy's fossil record, and reading it, an enterprise now called Galactic Archaeology, lets astronomers reconstruct the Milky Way's assembly, merger by merger. The single most consequential measurement one can make of a disk galaxy is its rotation curve, the orbital speed of its material plotted against distance from the center. Newton's laws give a simple expectation. If nearly all the mass sat where the visible stars are in the bulge and inner disk, then beyond the luminous edge the orbital speed should fall away, with distance gently, just as the outer planets move more slowly than the inner ones around the Sun. That decline is called Keplerian, and it is what a galaxy made only of its visible matter would do. It is emphatically not what galaxies actually do, and the discovery of that fact is one of the great turning points in the whole history of physics. The thread runs from Fritz Zwicky, who in 1933 found that galaxies in the Coma cluster were moving far too fast to be held together by their visible mass, and coined the term dark matter, to Rubin and Ford, who from the late 1960s measured the rotation curves of spiral galaxies with painstaking spectroscopy. Their study of the Andromeda galaxy and their landmark survey of 21 spirals in 1980 showed that rotation curves stay flat, the orbital speed holding roughly constant, out to the very largest radii they could observe, far beyond where the starlight fades to nothing. A flat rotation curve carries a stark implication. The mass enclosed must keep growing in step with the radius, even out where there are almost no stars to supply it. There must be a great, extended, invisible reservoir of mass, and this is the dynamical cornerstone of the entire case for dark matter. Measuring our own galaxy's rotation curve is harder, precisely because we sit inside it and must painstakingly gather distances and speeds for tracers across the disk. Using tens of thousands of luminous red giants charted by the Gaia mission and its partners, astronomers have produced the most precise Milky Way rotation curve yet, finding the circular speed at the Sun to be about 229 kilometers a second, and the curve staying very nearly flat out to 25 kiloparsecs, itself firm evidence for a dark halo, since the stars alone would give a falling curve. Intriguingly, the latest data, reaching still farther out, suggest that beyond about 19 kiloparsecs, the curve does at last begin to decline in the long-awaited Keplerian way, marking the edge of the dominant mass, and hinting at a total mass somewhat lower than older estimates, though the galaxy's full weight, dark halo and all, is still reckoned at around 1 to 1.5 trillion suns. It is worth being precise about what all this does and does not establish. What is firmly established, not just in the Milky Way but across thousands of galaxies, in the motions of galaxy clusters, in the bending of light by gravity, and in the afterglow of the Big Bang, is a mass discrepancy. The gravity needed to explain what we see vastly exceeds what the visible, ordinary matter can supply. Within the standard model of cosmology, this is resolved by cold dark matter, a non-luminous, non-atomic form of matter making up roughly 85% of all the matter in the universe. The Milky Way's flat rotation curve, the orbits of its satellite galaxies, and the streams threading its halo are all consistent with our galaxy being the luminous core of a dark halo weighing about 1 trillion suns. What is not established is the nature of the dark matter itself. Decades of searches, detectors buried deep underground, hunts for its annihilation in space, Attempts to make it in colliders have so far failed to catch a single particle, and the once favored candidates have been squeezed hard without a confirmed signal, driving attention toward other possibilities. This impasse gives room to a genuine alternative. The idea, called modified Newtonian dynamics, that below a certain tiny threshold of acceleration, the law of gravity itself changes, so that flat rotation curves arise with no hidden mass at all on the scale of individual galaxies. This idea captures the rotation curve regularities with uncanny accuracy. A real, and not yet fully explained, pattern in the data that any complete theory will have to reproduce. Yet the weight of evidence favors particle dark matter, and it comes from places where rotation curves play no part. In the Bullet cluster, two galaxy clusters that have smashed through one another, the hot gas, which carries most of the ordinary matter, was slowed and stripped in the collision, while the gravitational mass, mapped independently by the way it bends light, sailed straight on with the galaxies. The mass and the visible matter ended up in different places, natural if most of the mass is dark and collisionless, but very awkward for any theory that ties gravity to the visible matter alone. And on the largest scale of all, the pattern of ripples in the cosmic microwave background is fit to exquisite precision by a universe holding about 5 times as much dark matter as ordinary matter, a number reached with no reference to any galaxy's spin at all. The rotation curve of the Milky Way is thus only one strand in a far broader web of evidence. The picture that results is a humbling one. The luminous Milky Way, the disk of stars, the glowing arms, the crowded bar, the sleeping black hole at its heart, is only the bright inner core of something far larger and almost entirely invisible, a roughly trillion solar mass halo of dark matter, whose particle identity remains the outstanding unsolved problem in the field. Even the density of that dark matter here at the Sun's position has been weighed, from the way nearby stars bob up and down through the disk, at a tiny fraction of a solar mass in each cubic parsec, a figure that matters keenly to the experiments on Earth trying to catch a dark particle as the Sun sweeps us through the halo. The galaxy we can see is the visible tip of a dark and far greater whole. It is fitting to end where the evidence is firmest, in the elementary dynamics that tie the whole portrait together. From the Sun's circular speed and its distance from the center, a single line of Newtonian reasoning gives the mass enclosed with the Sun's orbit, about 100 billion suns, comparable to the entire stellar mass of the galaxy, with dark matter taking an ever larger share farther out. The same reasoning, applied to a flat rotation curve, shows the enclosed mass rising in lockstep with the radius even where the starlight has died, the dark matter argument in its starkest form. And the mass weighed from S2's 16-year orbit predicts a black hole shadow of just the size the Event Horizon Telescope went on to image. 3 utterly different measurements, the enclosed mass, the rising curve, the imaged shadow, converge on a single, consistent galaxy, the one great spiral we can never step outside to see, and yet have come to know from within better than any other in the universe.